Hello, everyone, to another episode of Nerd RX podcast, and I'm your host, Barkha. Last month, the Nobel Prize in Chemistry was shared between three scientists, Carolyn Bertozzi, Morten Meldal, and Karl Barry Sharpless, for their contributions on click chemistry and bioorthogonal chemistry. And coincidentally, we have someone to talk about it today. He is none other than my former mentor, Dr. Umberto Battisti. Dr. Battisti was actually the first person to teach me my very first chemical reaction. So he is a very special person to me. And thank you so much, Dr. Battisti, for giving us your time and being here for this episode. We all are so excited. And welcome to the show.
Nice, thank you.
So, before we get into the topic, why don't you introduce yourself to our listeners?
Yes, so hi everybody, hello everybody. So my name is Umberto. I am an assistant professor at the Department of Drug Design and Pharmacology at the University of Copenhagen in Denmark. And my main background is medicinal chemistry. So I am a PharmD PhD. So I got my PharmD in Italy at the University of Modena, and I got my PhD at the same university. After that, I spent a few years working again in Italy in different laboratory as a postdoc. And in 2015, I moved to US, where I was actually working with Barca at Virginia Commonwealth University under Professor Glennon, where I was a lab manager. And it was a funny period. We were mainly working on drugs like MDMA or other type of amphetamine. And after US, I think I lived in US for 2 years. Then I moved to Sweden, where I work as a senior researcher at the University of Gothenburg. And since 2019, 2018, I'm actually here in Copenhagen, where I am an assistant professor, and I have even my own company, again working mainly in the orthogonal chemistry field.
Well, thank you so much for that introduction. My first question would be what is bioorthogonal chemistry? Because I remember when you were at VCU, we were like purely doing synthesis. So, how did this sudden change of field happen to you?
So, first of all, what is biorthogonal chemistry? So, biorthogonal chemistry is any type of reaction that has some specific properties. In particular, it has to be orthogonal to everything in the living body. So, that's the term biorthogonal. What does it mean? That it doesn't have to react with anything in the organism. So, it means that this reaction can actually happen inside your body, inside a human body, or inside a living cell. And there are different type of biorthogonal reaction. And as I said, one property is the selectivity. The other is the speed. This reaction has to be really efficient, so work and extremely fast in terms of second or millisecond. Another parameter is they have to work at extremely low concentration, so even below milligrams, so even at micrograms, because what we want to use this reaction for, not all the time we use a lot of compounds, so they have to be really efficient and work at extremely low concentration. And as I said, mainly they have to work in a living organism. And why I moved to bioorthogonal chemistry, I mean, I started a little bit working in this kind of field in Gothenburg. We were doing some modification of some protein with bioorthogonal chemistry. And then when I moved to Copenhagen, actually our main or my main field became actually the tetrazine ligation. That is the most important bioorthogonal reaction and the most used. It's because it's extremely fast, it's extremely efficient, and I was really intrigued by the fact that you can actually make a reaction in a cell or in a living organism, and it works at so low concentration. So it's really surprising if you think about it, that you can really form something into an organism, in a very controlled and designed way. So we can actually design the molecules we want to do. We can fashion the molecule. So it's very nice, I think.
Yeah, so it does sound unique that you can do a reaction in a living organism. So, why would you want to do such a reaction? What are the applications of this?
So the application of biorthogonal chemistry are manifold. So there are really several applications. So just from the top of my head, I can maybe tell you few. So the first one is just to, for example, modify, I don't know, a complex structure like nanoparticles or antibody, introducing, toxin on the antibody, or introducing some particular feature on the nanobodies or the antibody. So this is just one type of application. Another type of application, it's so-called click to release. So it's a very specific type of orthogonal chemistry when these two molecules react with each other, and then one of the two molecules, after the reaction, it's this reaction enables the release of an agent. This is actually employed nowadays in the clinic. It's been studied to safely vehicle toxins to cancer cell. So it's very nice. I think that it might be the future of biorthogonal reaction, or at least one of a very good application that might reach the clinic, because again you can basically cage, in a way, like protect your molecule in a way that your molecule is not active, and you inject your molecule or whatever. After the molecule reach the position where it's supposed to be, you inject the second component of the biorthogonal reaction, and this trigger the release of your agent. And this agent can be, as I said, a toxin, a cytotoxic drug, anything. And this allow you to safely deliver these drugs or this toxin to cancer cell or to an organ or whatever. So this is a very, very nice application, and I think it will have a big impact in the future. And the third application, just in the top of my head, that is actually what we work here in Copenhagen. It's called pre-targeting. So we use this pre-targeting approach for PET imaging. And PET imaging, it's a diagnostic technique based on the decay of radionuclides, so radioactive atom, that permit to, visualize or monitor different type of disease, from cancer to neurodegenerative disease to metabolic disease, and it's actually growing quite quickly. And the main advantage of pre-targeting PET imaging is that you can combine short live radionuclide like fluorine 18 with for example, antibodies. So usually when you use an antibody for PET immunoimaging, the antibody has a very high specificity, so it's easier to be produced compared to a small molecule, so it's faster, the production of an antibody. The main problem is that this antibody will float in your blood for a few days, and this is a problem because you need to use a radioactive atom that decays slowly, so it might take days to decay, but that means that you will have a major exposure to radioactivity. So what we do with pre-targeting, we combine the specificity of antibody with the quick pharmacokinetic of small molecules. So how it works in principle, we basically tag this antibody with one component of the biorthogonal reaction. Then we inject the antibody. The antibody, after few hours, few days, reaches target, and they start accumulating at the target site. Then we wait another couple of days so that the antibody is actually removed from the bloodstream, and at this point we inject the second component of the biorthogonal reaction. And the second component, it's a radio label, that means as the radionuclide, so the radioactive atom on it, and as usually the property of a small molecule. So this small molecule that is radio labeled reach very quickly the tumor site, or the site where the antibody accumulated, and it can only react with the tag present on the antibody. And in this way we can actually image the target of the antibody. And as I said, the very nice thing about this approach is that combine the very good property of an antibody with a fast pharmacokinetic of a small molecule. But again, these are only the three approach. They just came up in my mind now, but there are many other applications.
Right. So you mentioned you can also target neurodegenerative diseases. So you have compounds that even cross the blood-brain barrier?
So what you can do is the same approach I described for pre-targeting, but with bispecific antibody. So these bispecific antibody are antibody engineered to recognize two target. One target is anything that can be in the brain, like fibril from for A beta or alpha synuclein that is involved in other different type of neurodegenerative disease. And the second target of this bispecific antibody, it's actually the transferrin receptor. This transferrin receptor, it's actually a receptor present on the blood-brain barrier that allow to transfer large molecule into the brain to transcytosis. So what happens is that we inject the antibody interact with this transferrin, it's shuttled inside the brain when it's released, and then we inject the second component of this of the biorthogonal reaction. Again, this is designed in a way that can reach quickly the brain, interact with the tag on the bispecific antibody, and again we can image a target in the brain for the neurodegenerative disease and so on. Another approach that is possible with the antibody, but in general with the large molecule that we are now starting to use, we just ordered the instrument. It's called Fuse. That it's a focus ultrasound. So it's a very very new technology that allow to open up the tight junction of the blood-brain barrier using focus ultrasound. That I know has been proved, or it's now being studied in the clinic. We will soon have a machine and we start performing this kind of experiment in rats or mice. So in principle, what it means that any large molecules can enter in a controlled fashion the blood-brain barrier, because with this machine we are able to open it for a few milliseconds and allow these molecules in. And from the first research, it appears that this blood-brain barrier opening is so quick that there is no damage. And as I said, it's actually being studied now in human.
Wow, that is quite fascinating. So, what, because you're using these radionuclides and I'm assuming these chemicals are toxic, what about side effects? Are there any off-site effects with these compounds?
So, as an organic chemist, mainly I would say that we are way more exposed to chemicals in the normal organic chemistry lab, because the amount of
Right.
compound or chemical we use, it's much more, and the risk is directly proportional to the amount of the compound you use. So the main problem with radioactivity is that it really depends from the radionuclide. So there are different type of radionuclide, and each radionuclide at a different type of decay. Based on the decay, they can emit different particles that can go from an alpha particle, that it's a big particle the size of an helium nucleus, more or less, beta particles, and gamma ray. So when you work with radioactivity, you need to know with what you're working, right? For example, alpha particle, they are shielded just
Yeah.
by your clothes, so you don't need really a protection. You just not really need to be
Hmm.
really careful, do not
Yeah.
inhalate this compound. When you use something that emit beta particle, you need to take more precaution, but they can be shielded again. The main problem is when you have something that decay with gamma ray. This is a bit more difficult because they go through most of the material, so you need to be careful. The other really important thing is the decay time. So
Yeah.
every radionuclide has a different decay time. For example, fluorine 18, we were speaking before, has a
Right.
decay time of 2 hours. That means
Hmm.
that every 2 hours, the amount of radioactivity you have, it's halved. So that you understand that the radioactivity with fluorine 18, it's going down pretty quickly. Other radionuclide has enough time of months. So, and if they somehow enter in your body, this could be problematic.
Right. So, would you mind taking us through the steps involved here? Because I'm assuming you are synthesizing these compounds, right?
Yes. So, in principle, as I said, let's say I will make an example of how we assemble everything for the pre-targeting PET imaging experiment. So you have to synthesize two components. The first component, and these two components are part of this reaction we use here that is called the tetrazine ligation. So one component is a tetrazine. So we need to synthesize this molecule and to synthesize a precursor for the radiolabeling. That means something that can be transformed into a radioactive compound. And then at the same time, we need to synthesize the second component that it's a transcyclooctane. So it's a very reactive molecules. We synthesize it in few steps. And once you have this molecule, you need to actually react it with the antibody. So you have to put your transcyclooctane on the antibody. And how you do that, there are different ways. You can do in a non-specific way, so just using a coupling, like any different type of coupling. We use here NH ester, so activated ester that react mainly with the lysine residue. This is a modification that is not site-specific. That means that you can know more or less the amount of tag you have of an antibody, but you don't know the position. There are other more complex way to do that, and you can, for example, derivatize specifically thiols, so cysteine. And in this way, you know not only the number of tag you have the antibody, but even the position. So both way are possible. Once you have your component A that need to be radiolabeled, the tetrazine, and your antibody that it's chemically tagged, what you do, you inject the antibody in your patient or in your animal that you're studying. You wait for 3 days so that the antibody accumulate at the right spot. Here we use a colon cancer model. So there is a model. I think it's a xenograph. So we use nude mice with no immune system, and we let a tumor grow, and then we inject our antibody. We wait 3 days. After 3 days, we radiolabel the tetrazine. So this component that is radioactive, we inject the tetrazine in the mice, and at that point, after 1 hour, we have an image. And this image, I mean, when it works, it usually show the tumor. So and that's how this whole experiment works. So it's a quite a, I would say that the setup is quite complex, but we have several paper out, and we can do it now with quite easily. So we have everything set up, and we are studying different type of tumors, different type of tetrazine, different type of tags, and we can use different type of antibody as well.
Okay. And what about the chemistry? Is the chemistry involved difficult or is it easy? Something like a click chemistry, some.
So the click chemistry, the term click chemistry, it's just because it click, right? So it means that the reaction take place without anything. And yes, once you have
Yeah.
your compound, but this tetrazine ligation, it is a click chemistry. But the problem is that you have to synthesize the components yourself, and the chemistry to get this compound is not so easy. There are few steps involved. The molecule are not so stable, so they are labile to different conditions. They can degrade and so on. And for example, for this transcyclooctane, you need some specific instrument. We have a photocatalytic instrument that they allow the photoisomerization of the cis cyclooctane to the transcyclooctane. So I would say that the chemistry is quite specific and challenging, and you need again even some specific equipment. So it's not something you can do in every lab.
Okay. And I have a very naive question. So, do you have to synthesize different molecules for different models? Like you mentioned, now you have colon cancer model. So, will that vary from, for example, lung cancer model?
That's a good question. So I think in PET imaging, uh, so of course, for example, we were speaking about brain. Of course, the properties of the molecules that
Yeah,
need to reach the brain is completely different from the property of a molecule that need to reach a tumor in the colon or in the lungs. That's for sure.
yeah,
Between the lungs and other type of tumors, there might be some difference. Usually, what we notice is that we need a very, very polar compound, so they have to have a very high polarity because in this way they are excreted pretty quickly. And when they are excreted pretty quickly, you
mhm,
gain in contrast because they reach the target, react with the tag, and then the excess or the unreacted molecule is just excreted. And that's what we see for most of the targets. Then of course you might need to optimize your second component, the tetrazine, for a specific target that we never tried
right.
with completely different organs, because of course when you do a xenograft, it's not an organ, it's something that is growing on the side
Yeah,
of the mice. So there might be some difference, of course, yes.
okay. And what would you say are the advantages and disadvantages of this technique?
So let's start from the advantages. Of course, it's safer if it for the patient because the amount of radioactivity you receive is lower and allow you to use short-lived isotope like carbon 11 or fluorine 18 that otherwise would not be used, cannot be used with antibodies. So this is the two main advantages. The main disadvantage is it's of course the complex setup. So you need to have two injection, and that I think is the main problem of this whole approach. So it might not be so easy to translate to the clinic because you need to inject the patient 3 days, and then he has to show up after 3 days for the second injection. And from a logistical point of view, is not or logistic point of view is not might be not so easy in an hospital, but again, this is something maybe in the future, but I see as the main limitation of this approach.
Okay. And let's talk about the costs involved. Is this a very expensive technique to set up in a lab?
Yes, it's very expensive. I mean, everything with radioactivity is extremely expensive.
Okay.
You need to have a specialized lab, specialized equipment, and so on. So this is already like if you don't have a cyclotron to produce the radioactivity or the radionuclide, this cannot be bought. This is millions of euros. So you need a specialized equipment. After that, you need a specialized lab. So you need a specific hood for radioactivity. So they are completely sealed. They are with
Okay.
and so this is the most expensive thing. After that, the chemical itself to assemble the two chemical stack, they are not very expensive. So that potentially can be bought from anybody and start assembling the component. As I said, you might need some specific equipment to synthesize mainly the tricyclooctanes, and this is some more expensive, but I don't know, 10, 20,000 US dollars. So it's still okay for a lab, I would say. And for the animal study, again, since you use radioactivity, you need specific equipment, you need the scanner, you need protection. And again, this is quite a bit of money. So I would say that if you have a laboratory already set up to work with radioactivity, it's not so very expensive. If you don't have a lab that can work with radioactivity, then it means a major investment. So really like major investment.
Okay.
So that's
Wow.
it, I guess.
Okay. Yeah. And so this is just because you're involved in this field so much and it sounds so unique. What do you see is the future of bioorthogonal reaction and PET imaging pre-targeting, let's say in next 5 to 10 years?
So for biorthogonal reaction, as I said, the main focus now is shifting toward this click to release. This, I guess, soon will reach the clinic. Will be a major advancement in some field because, as I said, allowed to release selectively molecules and in a controlled fashion. And these allow you to use extremely toxic compound and deliver and control the delivery in a specific organ or in a specific place. So this will be, I think, the future in general of bioorthogonal chemistry. Regarding pre-targeting per imaging, I think that nowadays many groups, including our, prove that it works. The problem is that with imaging, so just visualizing the tumor, this whole approach might be too complex and too expensive. So what can happen is that we're going to use the same approach for therapy. So we're going to use the same approach I described, but instead of using a radionuclide that can actually be used to visualize the tumor, we are going to use a radionuclide, so an atom that decay that can destroy the tumor. So if we can prove that this is safe, it works, then this might be the future of pre-targeting. So not imaging, but imaging and therapy. So this is called pre-targeting theranostic. So that you have something that can be used for both the diagnosis and the therapy.
Okay, and as always, my last question to you is, can you suggest a few articles or resources for our listeners so that I can list them down in the description for everyone?
So, as I said, our group or my group has been very active in the pre-targeting PET imaging. You can, of course, feel free to search for my name or my current PI that is called Matthias Earth. We have several paper out on this subject. Regarding click to release, the main there are two main group working on this. One, it's a company that is called Tagworks from the Netherlands. So you can search article from this company. And the other group is the group from Professor Hannes Mikula in Vienna, Austria. And again, they are really active on biorthogonal chemistry and click to release. So I would say you can browse this, and there are some really nice review, I think, in chemistry reviews about biorthogonal reaction by Oliveira et al. I think it's a 2016 paper, so you can just check. And this very comprehensive review on biorthogonal reaction, how they works, what they can be used for, application, and so on.
Well, that is it for today's episode. It was a very unique and I think my first chemistry based episode. And I learned a lot. Thank you so much, Dr. Battisti, for giving us your time.
Thank you for the possibility to speak about this, and thank you for everything.
Thank you so much. And listeners, I will catch you next week. And if you have any suggestions about topic, or if you want to come on this podcast and talk about a technique, please feel free to email me at barkha@nerdrxpodcast.com. And remember, it's good to be a nerd. Bye.